So we come to the last lecture in this sequence from Mathematics 220, and the topic of this lecture is more infinities. So we've shown in the last couple of videos something about the infinity of the natural numbers, namely denumerable sets. We saw it was quite robust, undertaking unions and intersections and Cartesian products. And then we looked at the infinity, which is just a bit bigger, or actually quite a lot bigger, namely the infinity of the real numbers. And we saw that the infinity of the real numbers is not the same, can't be put in bijection with the infinity of the natural numbers. And that's Cantor's very, very famous diagonal argument shows you that. And so what we want to go on to now is, well, now that we've shown that there's more than one infinity, namely that there are at least two infinities, it's a reasonable question to ask, well, how many are there? And that's the topic that we're looking at today. And we're going to do that by examining something called Cantor's theorem and the more infinities that Cantor's theorem implies. But before that, let's just recall that we've shown that, well, we know that the natural numbers are a strict subset of the real numbers, and we proved using Cantor's diagonal argument that the natural numbers are not in bijection with the real numbers, so the real numbers are definitely larger. Now we'd like to be able to state this a little bit more precisely. In particular, we'd like to be able to state something like the following, that the size of the natural numbers, indicated by this Aleph naught, to denote the cardinality of the natural numbers, is strictly smaller than the cardinality of the real numbers. And we want to make sense of what does this symbol actually mean rigorously in the context of comparing infinities. Okay. So we can make this precise by extending ideas that we had for finite sets A and B, namely if we can construct an injection from A to B, then we know that A has to be smaller than B. Okay? So this is what it meant if we could construct an injection from one to the other. On the other hand, we know that if we can construct a bijection from A to B, then we use this to actually mean that these sets are equinumerous. So by combining these two things, we can give a rigorous definition to this symbol here in this context. Namely, what does it mean for this infinity to be strictly smaller than that infinity? So let's give ourselves a definition here. So let A and B be sets. Then we write the size of A is smaller than or equal to the size of B when there's an injection from A to B. That's how we make this symbol rigorous for infinite sets by saying, hey, there's an injection from one to the other. And this is taking that idea from finite sets and extending it across to infinite sets. Now, we can push that a little bit further to say that the size of A is strictly smaller than the size of B when there's an injection but no bijection. So when there's an injection, we know it's less than or equal to, and when there's no bijection, we know that it can't be equal to. Okay, so this is the same as saying size of A is strictly less than the size of B, if and only if the size of A is less than or equal to the size of B, and the size of A is not equal to the size of B. So there's an injection, but no bijection. And so we can use this to make rigorous statements about one infinity being strictly smaller than another. Now, Cantor's diagonal argument proved for us that Aleph naught, the size of the natural numbers, is strictly smaller than the size of the reals, the continuum, and so we've given a strict meaning to that symbol, so that this means there's an injection from one to the other, but no bijection. Now, first good question to ask here, we've already seen that there's no infinity smaller than the natural numbers, because any subset of the natural numbers is either finite or denumerable itself, so there's nothing smaller than this infinity. And we've shown that this infinity is bigger. So a good question to ask is there anything that sits in between here? So more precisely, is there any set A that sits strictly in size between the naturals and the reals? And this particular question is formulated as the Continuum Hypothesis. And this was a conjecture first stated by Cantor in 1878, that there is no set A, that there is no infinity that sits strictly between the size of the natural numbers and the size of the reals. That there's nothing here. Now this is a very, very weird statement, and it resisted proof for quite some time. And indeed, Gödel came along in 1940 and proved that you cannot disprove this statement using any of the standard bits of set theory like we've been playing with in this course. So you can't disprove it using standard bits of set theory. Now it gets a bit weirder because along came Cohen in 1963, so 20 odd years later, and showed that you cannot prove it either using the standard bits of set theory. So using the techniques that we've been playing with in this course, you can't disprove this statement and you can't prove this statement either. And so, I mean, this, even though quite a lot's known about it, it's probably not so correct to call it a conjecture, and that's usually why it's called the Continuum Hypothesis rather than a conjecture. So it's a very, very weird statement. Okay, so there's no infinity that sits between the naturals, excuse me, between the naturals and the reals. Good question, is there anything bigger? So, are there bigger infinities? And this we can prove to be true using what's now known as Cantor's theorem, which was published in 1891. And it says something pretty straightforward, at least for finite sets, namely, let A be any set, then the size of A is always strictly smaller than its power set. Okay, so taking the power set of a set definitely gives you something bigger in a way that unions, intersections, Cartesian products did not. So this is an operation that you can do to a set that always gives you something bigger. Now, in order to make this work, we've first got to prove that it's less than or equal to, and then not equal to. So this means we have to find an injection, and then that there's no bijection. Okay, so excuse my handwriting here. This means we have to first prove that there's an injection between the set A and its power set, no matter what the set is, and that you cannot build a bijection. Now, of course, we should take note here, if A is finite, then this follows pretty directly. In fact, if A is size n, then the power set of A has size 2 to the n. That's a relatively easy proof. So we're more going to concentrate on the infinite case, because the finite case isn't so exciting. But we can quite quickly and easily find an injection from A to its power set. So here are two simple examples. We can take the set function f, which takes the set A to its power set, so namely it takes elements of A and turn them into subsets of A. And we can do that just by taking any element and turning it into the set that contains that element. Another good example of this is we can take function h, which takes A, turns it into, it maps into the power set of A, just by taking the complement of this. So the image of any element is the set of all elements except that. And this, with a little bit of work, you can prove that these are both injective. That's not too hard. It's not a bad exercise. Now, this proves that the size of A is less than or equal to the size of the power set of A. Not something terribly surprising, but something we need to do a little bit of work to. Yeah. So we probably should prove that one of these is an injection. Probably the first one here is the easiest one. Now, we prove that there's no bijection, so that these sets can't possibly be in bijection with each other, not by proving that there's no bijection directly, but instead showing that there cannot be a surjection from A to its power set. So if there cannot be any surjection at all, well, then there can't be a bijection, because a bijection needs to be both an injection and a surjection. So we're actually proving, I guess, something a little bit stronger here by showing that there can't be a surjection. Now, how does this work? Well, to explore the main mechanism of the proof, let's just consider a finite set 1, 2, 3, and consider those functions f and h from the previous slide. So notice that the function f takes an element and turns it into the set that contains just that element. So 1 maps to the set that contains 1, 2 maps to the set that contains 2, 3 maps to the set that contains 3. The function h, on the other hand, takes the element 1 and turns it into the set of everything except 1. Set the number 2 turns into the set of everything except 2, 3, everything except 3. Now, these functions are opposite extremes, and I've constructed them to illustrate a point. So notice that for the first function f, no matter which element we pick, that element is always in its image. 1 is always in its image, 2 is always in its image, 3 is always in its image. Because remember, we're taking a set A and mapping it to the power set of A. So we're taking elements of A and turning them into subsets of A. And so we're really saying that, hey, every element x is in its image under the function f. On the other hand, for the function h, we have the opposite thing. 1 is not in its image, 2 is not in its image, 3 is not in its image. And so for all x in A, x is not in its image under h. Now, more generally, if we have some function g taking me from A to the power set of A, then if x maps into its image, let's call it a good point, at least for the purposes of this proof. So if x maps into its image, like here in f, then we'll call them good points. And if x is not in its image, then we'll call them bad points. So under f, every point is a good point. Under h, no point is a good point. Every single point is bad. So we can build the sets of all the good points and all the bad points. So let G be the set of all the good points, all the points that map into their image. And let B be the set of points that don't map into their image, so namely all the bad points. Now, notice that G and B are both subsets of A, and so G and B are in the codomain of our function. We're going to use that, the fact that if we want G to be surjective, something has to map to those to make this proof work. So, also notice, of course, that G and B are complements of each other, so that G intersection B is the empty set, and that G union B is equal to the whole set. No, whole set, power set of A. No, it's equal to the whole set A. Okay? So we have these two little facts here. All right, so let's go on to the proof, or at least how to make the proof work. Now, as often is the case, the bad set is more interesting. So let's assume to the contrary that we can construct a surjection from A to the power set of A. Let's call that G. And let's build the set of all the bad elements. So all the elements in A that don't map into their image. This is some subset of A. Now, because this is some subset of A, this set B is in the codomain of our function. Okay? So B is an element of the power set, precisely because it's a subset of A. So this B is an element of the codomain of our function, and since G is, by assumption, surjective, there's got to be some element in A that maps to that element of the codomain. So there's some little b that maps to big B. So the set of bad points is the image of something in our set A. Now, to get our contradiction, we ask ourselves the question, is B in capital B or is little b not in capital B? That is little b good or bad? Now, if little b is good, then little b is in its image. But then if little b is in capital B, the capital B is everything that's not in its image. And so when little b is in big B, by the definition of big B, we must have that little b can't be in big B. So we get a contradiction. On the other hand, when little b is not in big B, little b is not in its image, and so by the definition of our set capital B, little b must be in big B. Again, giving a contradiction. So I suggest you work through these 2 points very carefully, but it means that little b can't be good or bad. Little b is not in big B, and it can't be in big B. So we get a contradiction here. So these contradictions mean that there can't be any such little b so that its image is big B. That means nothing maps to big B, but that means we have something in the codomain of our function which is not the image of anything in the domain of our function, and that means G is not surjective. So we have a contradiction. This contradiction means G can't be surjective. Well, since G can't be surjective, and we've constructed an injection from A to the power set of A, in the previous slides, and G, we can't make a surjection, that means we can't make a bijection between these two sets. So there's an injection but no bijection, and so we know that A has to be strictly smaller than its power set. And notice this immediately gives to us that the set of natural numbers is smaller than the set generated by finding the power set of the natural numbers. Natural numbers is smaller than its power set. Okay, now with a bit of work here, you can actually prove that the size of the power set of the natural numbers is actually equal to the size of the reals. In order to prove that, you need something called the Cantor-Schroeder-Bernstein theorem, which we're not going to do here. But you can actually prove that the power set of the naturals is the same as the size of the reals. Okay, so notice here we've proved, back here, go back another slide, that for any set A, it's always strictly smaller than its power set. So there's some good consequences of this. We know that for any set A, it's strictly smaller than a power set, so that immediately tells us that the naturals are smaller than the power set of the naturals. Well, we can do that again. I can form the power set of the power set of the naturals. This is just some set, so I can form its power set. So we know the naturals, which is infinite, is smaller than the power set of the naturals, which is a bigger infinity, is smaller than the power set of the power set of the naturals, which is another bigger still infinity. And we can do it again to get ourselves 4 infinities. The naturals, the power set of the naturals, the power set of the power set, and the power set of the power set of the power set. And of course we can keep going here and keep getting bigger and bigger infinities. And so we get this wonderful corollary to Cantor's theorem, namely by keep on doing this again and again and again, we get that there are an infinite number of different infinities. This is a fantastic result which shows that infinity is not at all what we thought it was when we first encountered it. When we first thought of infinity, we thought it was just a set that kept on going. Cantor's diagonal argument shows you to know that there's something bigger, that the real numbers can't be thought of that way. The real numbers are not denumerable. Then Cantor's theorem, which we've just proved, shows you actually you can keep making bigger and bigger and bigger and bigger infinities just by starting with the natural numbers. Let me uncover this proof here. Starting with the natural numbers, Cantor's theorem tells you that the power set's always bigger, so that the power set of the naturals is bigger than the power set, bigger than the naturals, so maybe I shouldn't have that there. So we can keep taking bigger and bigger sets by continuing to take the power set of the power set of the power set. And so by repeatedly taking power sets, you can create an infinitely long sequence of larger and larger infinite sets. And so we have an infinite number of different infinities proved to us by Cantor's theorem. So this is probably where we're going to stop here in this course. In fact, it is where we're going to stop in this course. But one of the things I want to just remind you of in this journey that we've done in Maths 220 is we've started with really basic definitions of sets and subsets, statements, logical operators, and truth tables. We've started from really very, very basic building blocks here. And look where we've gotten to in the course of a term. We've proved the diagonal argument, Cantor's diagonal argument, namely that there are different types of infinities, which is really a contradictory result and tells us something very fundamental about the universe around us. And then we've proved Cantor's theorem just in this slide, which tells us that there are actually not just two types of infinity, but there's actually an infinite number of different infinities. This is a really fundamental fact about the universe that we've been able to prove starting from something as basic as truth tables, and we've reached this within one term. And so if you've been following along here and kept up with all of this stuff, really, congratulations. This is a really fantastic achievement to get from where we started to where we've just managed to get to in one term in Mathematics 220. So really, give yourselves a pat on the back for getting this far in the space of just one term. And that's where we're going to stop. Thank you for listening.